All right, in this example, we're still doing friction loss calculation, reviewing actually. So some examples will be related to hydraulics, others are general fluid mechanics, such as this example that you see here. So we have a water tank, and I'm saying that because if you recall when we discussed how we find the friction loss coefficient F. Let me just pick my pointer. There we go. So discussed F. We said for turbulent, I believe this example will have turbulent flow. So in order to find F, we can use the Blasius equation, but that would require that the Reynolds number has to be less than 100,000 and smooth pipes, which I believe they are, but I don't think we're going to meet this condition, so we will have to use the chart. Again, this is a general fluid mechanics example. It's not hydraulic, but still it's the same concept. Nothing changed, just the numbers are slightly different. So we have the water tank here at an elevation of 30 feet at this point. Let's call this point 1. And this is a tank. It's moving at a rate of 2 cubic feet. So Q dot is 2 cubic feet per second. We need to find the pump requirements, which include the head in feet or inches, the pressure head in PSI or pound per square foot, and then we need to find the power. We'll try to find it in horsepower. To overcome the static head difference, the friction losses, so to overcome all the obstacles which we will find or to meet the requirements that are listed here. What are these requirements? They're a mix between the sketch and what you see up there. We need to lift it, and that's the first one, the static head difference. We need to lift the water from the tank, which is at an elevation of 30 feet, all the way to Z2, so that's 0.2, 60 feet, or we can say Z2 minus Z1 equals to 30 feet, okay? Just note Z2 minus Z1 because, again, as we discussed last time, the difference might be Z1 minus Z2 or Z2 minus Z1, depending which side you're working with. We have 4 standard 90-degree elbows. We have 2 gate valves before and after the pump, and that's usually for maintenance or if you want to change the pump. So we have one here, and we have another gate valve, and they are wide open. And also we have a check valve. They didn't say where, but usually we put it on the discharge pipe here. And that's when the pump is shut. Let's use the symbol that we're familiar with. So the water doesn't go back, and it helps in priming or starting up the pump. So it would look like this. Which has a K value, K equals 4. So they gave you that. So if it's not matching with the table, yeah, usually K is equal to 2. I'm not sure if I changed that or what do you have it on your notes? Is it 2 or 4? That K for the check valve. What did I give it to you? Not the table, not this one.
It's 4
K,
for the
K
example.
equals 4.
It's 4. Okay. Ball check valve. Okay, 4. That's good. I don't know why on my old notes that table is 2. All right, that's good then. Both pipes are smooth. Hopefully I used it 4 as well in my calculations. Otherwise, we'll need to do extra calculations here. All right, what's the first step? We have the sketch. We labeled everything. It seems we have the assumptions. We have them also. You can write them here. So point 1 and 2, which is here, both are atmospheric pressure. So P1 equals, again, I don't need to go through the exact details. Is it gauge, absolute, because both are absolute. They're open, both are atmospheric pressure. So they're going to cancel from my Bernoulli's equation. So it's P1 over gamma. We have water, so that's gamma water, plus Z1 plus V1 square divided by 2G plus the head of the pump minus head loss. I don't have any motor, so I'll skip that. Equals P2 over gamma plus Z2 plus V2 square divided by 2G. So those two, the two pressures, they're going to cancel this with that because both are atmospheric. What did we say about the tank? We said any tank with respect to the flow inside the pipes, the velocity. When we compare the two velocities, this one is too slow, so we can't see it really moving. I mean, or it can be neglected, especially when you say V square. And if you look at point 2 this time, that's the velocity of the flow inside the pipe. So if you compare this one to this, you can see V1 will be V1 is much less, but V1 square is triple, since it's square, not triple, but it's much more less than the velocity inside the pipe. So we can neglect this one. Okay. We will need to find the velocity, Z2 and Z1, we have it. We're looking for the head of the pump. So I think we're good in terms of that equation. I can rearrange everything. So first, the static head, it's Z2 minus Z1. I'll take Z1 to the right side. I'll take the head loss, and then V2 square over 2G. Before we do any calculation, so let's look into this equation. What does it mean? So the pump needs to supply the elevation difference. So it needs to lift the liquid from Z1 to Z2, and that's why it's a positive value here. Again, we're trying to find the required head for the pump, which would give us the pressure needed and the power. So if Z1 was above Z2, then we will have this as negative. So it decreases, or it helps the system by reducing the pump requirements. So it needs to overcome the static elevation difference. Also, it needs to overcome any frictional losses, the head loss. And it needs to supply or give us an output velocity at point 2. Okay? We have the first one, Z2 minus Z1. It's given, so that's the easiest one. Before we start working on the head loss, we always need to start with the velocity, because we need to determine what type of flow is that. Is it laminar or turbulent? So let's go ahead and find the velocity of the pipe, which would be equal to V2 as well. Okay, that's the flow rate, Q, divided by the area, and that's given here, the length, both length and diameter. The length here, we'll need it later, but now we need the diameter. So it's Q dot. It's already in cubic feet, so I don't need to do any conversion. Usually it's given in gallons per minute. Let's clean this a little. All right, the area is pi over 4. So I'll multiply here by 4 times the diameter, 6 over 2. So that's 0.5 square. This would be in foot square. This would be in cubic feet per second. So we'll have the velocity in feet per second. I got 10.18 feet per second. Next, we'll find the Reynolds number. That's 7740 VD. We're missing the kinematic viscosity. We need the viscosity for water. So we can get that from some references. For water, it's almost at standard. Yeah, it's 60 degree here. It's almost 1 centistoke. So it would be 7740 times 1018. Again, make sure you're following the units that are given. So the velocity has to be in feet per second, and that's the velocity inside the pipe. Since there's no change in the diameter in the whole system, so I don't need to calculate one here, and do that multiple times. The diameter has to be in inches, so it's 0.5, 6, not point. Six inches. And here we'll use 1. So the dynamic viscosity is 1 centistoke. And this would be, excuse me, 472,759. As you can see, it's above the 100,000. So it is turbulent. First, let's delete that. So first, it's above the 4,000 limit. So it is turbulent. Now, if I need to find F, then what we have in this course, we have the Blasis equation. That's if it's smooth, which I already said it is. It's given here. But the Reynolds number has to be less than 100,000. Okay. If it's above, then usual, I'll need to use the Moody's chart, or I can use this one. The chart that you can see here, which is on page 41. So we have 470,000. That's here, 100,000. So 2, 3, 4, almost 500. So in between those two. So go up until we hit, again, what's that chart? Sorry, the curve. This is for smooth, and that's the only one we have. So if the pipes are not smooth, so we'll need to find some other references to find that. If we do this, I got a value of almost 0.1013 or 4. Okay. Again, it's somewhere slightly below that number. So yeah, you can add on 5.0135. It seems it's going to be in between those two. Anyway, we'll get F, or since I'm here, if it was less than 100,000, so I can use the Blasis equation. If it's turbulent, if it's laminar, then it's 64 divided by the Reynolds number. And that's why I like this summary sheet, because it helps us in these steps. So I have the table here, so I'm going to just write here, F is 0.013. Actually, I did put on my notes 33, because again, it seems slightly above the 0.013. Therefore, the head loss, the friction head loss, I'll use the Darcy's equation, FL over D, V square, V pipe square over the average usually. I mean, always we'll use the average. So it's 0.0133, that's F. The length, we have it as 1200 and 1500, so that's 1700. Feet, divide by 0.5 feet to meet feet and feet together. And then 10.18 squared divided by 2 times 32.2. So the head loss due to friction will be, my calculations are correct, I'll get 72.77 feet. You should see on your notes that chart on the next slide. Do you?
Yes, it's on the next slide.
Okay, thanks. These are slightly, because I have the updated one on the shared drive, which I don't have right now because we were supposed to be on Wednesday. Anyway, I did update that. It's easier to go back and forth. But anyway, you should get that number if you do it. All right, next we'll find the friction loss and the fitting. So we have the valves. We have 4 90-degree elbows. We have one here. 1, 2, 3, 4. We have 2 gate valves. So we'll need to pick the values for these if it's not given. The check valve is given for us. And sometimes I do put the entrance depending if we have it in the table or we don't. So in fluid mechanics, I do it because I have an extended. Let's see, I don't have it here. So I might give it to you if it's in an exam. Yeah, I didn't because you don't have it, but we can always go to some references, add here, for example, the entrance, because there is some K value, and report here and add it to the final value that we get here. All right, we have 4 90-degree elbows. The K for that is 0.9 each, so it's 3.6. We have 145 right there after the pump. Only one, so we'll pick also the value. The gate valve wide open, 0.19, we have 2 of these, and then the check valve, it's given as 4. So again, since the system doesn't have any change in the pi in the diameter, so I can simply say the head loss for the fittings, which I use HLV, it's summation of all the K values, and then multiply it by V squared over 2G instead of doing each one by one. Okay? So from here, this would be 8.4. The velocity, 10.18 square over 2 times 32.2. Okay. Let's see. $13.5 feet. Therefore, the total head loss will be 86.3 or 29 feet. All right. So we're almost done. The head of the pump then is Z2 minus Z1. I'm not going to write the whole equation. We have the elevation, then the head loss, then the velocity. So it's 30 feet plus the head loss, 86.29 also in feet, just to make sure we have all units matching. Then we have the velocity, 10.18 square foot square per second square divided by 2 times foot per second square. So we'll have also in the answer in feet. I got my notes, 117.9 feet. All right. If it was directly the horsepower, we can use this equation. Again, we did this last time. So we have two options. So it's the hydraulic horsepower of the pump times 3950 divided by Q, but Q has to be in GPM times the specific gravity, which is 1. So I can find the hydraulic horsepower for the pump, right? Just make sure you convert the Q into GPM. Or we have the other option, which is the hydraulic horsepower. It's delta P and PSI times Q again. So we have to convert anyway Q into GPM. But if you want to use this equation, so you have to find delta P for the pump, which is needed. But I'm saying if we only need the hydraulic horsepower, you can skip one step and directly use that equation. Okay. Let's do it here. So first, delta P. Let's skip the units for just a second. This is going to be first in pound per foot square. So that will be gamma H. We're doing the pump, so gamma HP. If you're doing delta P loss, the pressure loss, so it would be gamma times the head loss. This one is 62.4. It's water pound per foot square per foot cubic feet. And then this one we said 117, right? 117.9 feet. So 7,356.96 pound per foot square. We'll divide it by 144 inch square per foot square. So this would that would give me pound per inch square or PSI. 51.1 or 0.09. I'm doing a lot of rounding as I move on, so I might end up with slightly different answer then. All right, the hydraulic horsepower now. First, let's do the flow rate. So Q in GPM is 2 cubic feet per second. I'll divide that by 0.00223. Wait, so 1 GPM is it that number? Cubic feet per second, I believe. In every GPM. So this with that, and then we'll have GPM at the end. $896.86 gallons per minute. Therefore, the hydraulic horsepower in HP, it's delta P times Q over 1714 would be 51.09 into Q over 1714. $26.7 horsepower. Any questions? All right. You can try the other one. I did get 26.7. The other equation should be a straightforward. All right. Next, we'll start with the last part of this chapter, which is losses inside valves in general. Actually, we're heading to the next chapter, which is valves, so not only one. But here, mostly, we're talking about flow control, how we can control the flow, and what are the effects of that on the pressure drop, and how we can control it, or how we can calculate that. Just as a quick reminder, we have three different, which actually we might start today. So we have three different categories for not flow control. For valves, one of them is flow control, the other is pressure control, and then we have direction. So this one we're talking about flow control, which includes two types: the fixed, which is the orifice, and then we have the needle valve. Each one has a slightly different equation in terms of this constant. So this equation gives us how we can control the flow with an orifice. It has a orifice coefficient, C, times the area times the square root of 2G times the pressure drop that happens before and after, divide by the specific weight. You can find all these, or you can also use some experimental data, which would give you a very similar equation to what we just did. It's Q equals K square root of delta P. Why is it the same? In fact, if you square both sides, you should get Q square equals K square times delta P. And then delta P will be 1 over K square times Q square. Remember, Q square is simply A times V. So if you combine K square and A square, so you will end up with, and of course, delta P is gamma. I'll delete those. So HLV equals A square over K square times V square. So if you take this down, And then this whole thing, you just call it K for the orifice or for the valve. You will end up with the same form that we just did for any valve or any fitting, right? But this is very specific for orifice. We have the K value, so you have to be slightly careful. You have the K value or something called the K equivalent. So the K value, this is the form for the equation, or we'll be using the other one, which is delta P equals Q square over K square. So this is K for the orifice or the needle valve. Okay. Or we can use what I just did, which is 1 over K square. We will call it K equivalent for that valve or that orifice. And then you have the equation because the relation is 1 over K square. So if they say K of the orifice, usually they would say K equivalent. They give it to you. And then they would ask you to find K. So be careful. You might have to do 1 over and then find the answer. We'll see this in the equations. But usually I'm going over this because the many manufacturers, they provide you with this K value. They provide you with charts for delta P versus Q. So you can always find the K by finding this relation or looking here, or they might give you some values for K somewhere else. But that's how it is. They give you delta P versus Q, not the head versus the velocity inside the pipe. No, we're more interested to know how much delta P we're incurring due to that flow passing through the orifice or usually a needle valve. Okay. Let's check some more details in this example. So we have an accumulator. I might need to do the calculations as we go, because example 8. Okay, I do have it. I have the updated one. That's good. So what do we have? We have a piston and it has a cylinder up there. And we're trying to push that cylinder up using an accumulator. So we have the accumulator. It's charged to 2000 regardless. Usually, I believe it also, okay, we'll discuss this more in the next chapter. So usually you would have a pump, but this pump will not be working 24 hours. It's not continuous. It charges the accumulator, and then the accumulator will be used to operate the system when needed. So the pump doesn't need to be on, and that saves actually energy. And that's one of the discussions that we'll do in the next chapter. But for now, we have this piston here on the right. It has a diameter of 2.5 inches. It's supposed to move up when the piston is actuated. We can't, we don't accumulate, not the piston, sorry, the accumulator. So how do we do that? We will need to give a signal to this directional control valve, DCV. We'll review those. We're actually heading there also in the next chapter. But this DCV has some losses which are given in terms of the K equivalent. We just said that. Be careful. Is it K equivalent or is it K? Because the equation is slightly different. Okay, so usually we would send a signal somehow to, we have here a solenoid. So it opens or switches the position of this. So the flow would go through the DCV into here. All right. So what's the role of the accumulator? Here it's used to If we have a pump, it's usually a backup pressure. That's usually. But in addition to that, you will find it in systems, it absorb any kind of fluctuation. So if the pressure, if we need, let's say, we're going to calculate that, but let's say we need here 1500 PSI, and the pump starts fluctuating, it gives you 1400, 1450, 1550. So this accumulator, it can absorb and give adequate pressure when needed. So it avoids or prevents or minimizes. I prefer minimize or reduces pressure fluctuations in the system. But for now, only in this example, since I don't have a pump shown, the main role is to provide lifting or provide adequate pressure for the system. But usually it acts as a backup source to provide enough pressure when the pump is down or when the pump is not working. Okay, what's the speed of the cylinder when it's, as we see here, so we don't have retraction, we're only doing extension. So what is the speed of the cylinder when the pressure right here, under a pressure of 500 PSI, we should probably, I should say, neglect frictional losses and other losses in the lines. So when the pressure at this point, I don't know what I called it, but let's just say point 1. So P1 is 500 PSI. What's the velocity of that piston? So to find the velocity, I'm going to need the flow rate that goes inside here and pushes up. Q is the area of the piston since it's pushing on the cap side, so it's the piston, which we do have it. It's pi over 4 d squared, so that's given. And that would be 4.9 inch squared. So we have this. So V piston times the velocity of the piston. So now the question is, what is Q? What's the flow rate, Q dot? If the line pressures, if line pressure and fittings, elbows, etc., let's just say elbows because the DCV is given since we have K equivalent. So elbows pressure drop are neglected. So let's look into the DCV. Delta P for the DCV is equal to K equivalent times Q squared, correct? We just saw that equation. It was given. We do have the K equivalent, 0.004. So now my task is to find delta P across that DCV. What's delta P? As you can see, if the accumulator is actuated, since we're saying the piston is moving, so it has to be on. That's going to be, and we're neglecting any pressure drop. That's why I said I have to make that assumption. So at this point, the pressure above upstream, this P, let's call it PA. It's PA minus P1. What's PA? It's 2000. The line pressures are neglected, minus P1, which is the pressure that's given, 500. So that's equal to 1500 PSI. So now I can find Q, and that will be, before we move, we have to check the units. Actually, they didn't give us the units for K equivalent in that example, but let me check. The units here are Where is Q? The first one, cubic inch per second. Okay. Because K does have, it's not like the other coefficients, it does have a unit which depends on delta P and Q. But assuming the pressure as in PSI, which is PSI, so that's good. Q and inch cube per second, we have that K equivalent. So Q will be delta P divided by K equivalent under the square root. So delta P is 1500 PSI divided by 0.004. That's equal to 612.4 cubic inch per second. The area is an inch square. So what we get for velocity, inch per second. V for the piston will be Q dot divided by the area of the piston. That's 612.4 cubic inch per second divided by the piston. And I got almost 125 inch per second. All right, any question? Usually this question, or this type of questions will be combined with what we see on the next slide. So they ask you to find the velocity, the flow rate, or there's an initial requirement that you will need to find, and then they would do a change in the system. Usually if we have a needle valve, as we'll see here, they will give you an initial value for that needle valve, which I believe you should see in the homework. Not exactly, but they would ask you to change the velocity, for example, in the homework, the velocity of the motor from whatever velocity to half, to double, and so on. So you will need to do some changes in the system. But before you do that, you will need to find the K value of that valve. All right, so what do we have here? Assume, and that's very similar to what we have here. I said the motor and the homework. Here we have a cylinder. So they're asking you to restrict the flow so that the speed is reduced to only 5% of that calculated value. What should the K value for this valve be? So I still have that actuated. So it's like that. Excuse me. So they're asking you to find, we added a needle valve. We're going to close it so that I can restrict the flow going into the cylinder to drop the speed to 5%. So V nu is 0.05 of V that we just calculated. Did we just call it V? Yeah, or VP. I can start from there and find Q, or since simple Q is the area of the piston times the velocity, so Q nu is 0.05 times Q that we calculated, which is 612.14. I believe. Yep, 612.4. Or 37. Yeah, 4. Okay. So 0.05, 612.4. That would be 120, 30.62, 30.62 cubic inch per second. So now I found Q here that passes through that. So the question becomes, how can we find K for that valve? And that's what's needed. So the question becomes, what's delta P? Why? Because again, we have that equation, delta P for the valve, the needle valve, is K equivalent times Q square. So Q new, since that's what I'm trying to do to find, or I need to find this K to give me the Q new. We worked the other way, so we're doing it backwards. We already found Q. We're gonna plug it here. So what is delta P across that needle valve? Do you know how to find, or do you have any idea how we can find now this delta P? So now this pressure, that's what we called P1. This one is what we called PA in the previous one. So now we have a new pressure right here at this point. So what's this delta P? If I can find that delta P, I can plug it there. I can find K equivalent, and then I can find K square by using the relation between K square and K equivalent. That's not a big deal. We can do that. But the question is, what's that new pressure right here?
Question.
Yes.
Where did you get the 612 from? I assume that was the Q from the previous.
Yes, this one.
Oh, okay.
Uh, that's the original problem.
Gotcha. Okay.
We calculated that. It's asking you to reduce the speed to 5%. We said the speed and the flow rate, they are directly proportional because the area of the piston is not changing. So if you do a 5% velocity, then it's going to also do a 5% for the flow rate, the volumetric flow rate. So that's how we multiplied this by that.
It's because you have to get the 5% of that value.
Yes.
Okay, gotcha. Thank you.
Before you go there, the question is why we want to find it is because I need to use this equation to find K for the needle valve. So we already found it. So now you go, oh, how can I find Q? So it's saying 5% of the velocity, so 5% of the original flow rate as well. All right. How do we find this pressure? So remember, we already have K equivalent for the DCV. So I can do for the DCV one more time, delta P across the DCV. It's K equivalent times Q. Which Q? Now we have a new flow rate times Q square, but it's new. It's PA minus, let's call it B. Hopefully I don't have a B somewhere. So let's call this point B, this one. So minus PB, and that's what we need. If I can find it, I can plug it here, and it would be PB minus P1. And then I can find K equivalent, because we have P1 given 500. All right, K equivalent, I have many now. I have two K equivalents. Let's call this K equivalent 1 or 2. This one is for the needle valve. K equivalent 2. And this one is what we had in the previous problem, in the previous part, sorry. So this would be 0.004. My Q value is 30.62 square. And that will be 3.75. And that's equal to PA, which is 2000 minus PB. Therefore, PB is almost 4, so it's 1996.25 PSI. Okay? So K equivalent 2 will be PB 1996.25 minus P1 500 divide by Q new 30.6 squared So it would be 1496.25 over 30.62 square. That will be 1.596. If you stop here, I would give you full credit for it. But since it's asking for the K value, so you will need to do an extra step. So K equivalent is 1 over K square. Therefore, K for that valve is 1 over K equivalent under the square root. Do I have an extra one? Yeah, I can write it here. And that will be 0.79. Any question?
Question. There was